All right, here we are for more regression. Now we're going to talk about the very important issue of checking conditions and checking for problems with regression analysis. A regression analysis is a bunch of little tools that we use, and very powerful tools that can be put together or used in different combinations. But in order to use any of these tools, we have to make sure things are working perfectly. Not perfectly. That I should retract that. That things are working well enough that we can make sense out of things. Whenever you are doing any analysis and you can't make sense of the results, that's a big problem, and you shouldn't be trying to use the results. Okay. So let's look at the conditions according to your textbook. Number one, linearity. The two variables should be related in a linear fashion. That usually means that on a scatter plot, the dots should be more or less an oval going up to the right or an oval going down to the right. Now, there won't ever be exactly an oval, but big blob, oval, something like that. Number two, the residuals should be nearly normal. Now that is actually related to number one and to number three. And number three, constant variability. At every point along the line, at every point along the values of x, for instance, the variability, the vertical variability, the variability in y, should be more or less the same. Now you can violate that to a certain extent, but if you violate it a whole lot, then you have problems. So, violating condition number one of the big ways to violate that is that you have a curvilinear relationship. Now, if you have a curvilinear relationship, it's not really a problem as long as you recognize it. If you don't recognize it, then you can't do anything about it. So, let's look at an example of some curvilinear relationships. The best description of x and y's relationship might be a curve. Sometimes, however, you can get really weird situations where it's not really a line at all. It's some kind of fluctuating thing. Maybe it's some kind of weird curve that's difficult to describe mathematically, etc. In those situations, regression is probably not what you should use. Even if there's a noticeable curve of any kind, you probably shouldn't use straight line regression, simple regression, which is what we're doing in this class. Now, there are ways to make sense of that. Regression definitely can accommodate this. A little bit more advanced methods can fit all kinds of curves and stuff to any kind of curved relationship, but in this class we won't. So just remember, if there's a curve, you can't use the tools we're learning here. They won't give you good answers. So here's an example that we had in a previous slide. You have a bunch of different schools represented as different dots. I can't remember why they were orange and blue ones from where I stole this graph from. A bunch of schools represented by these dots, and on the y-axis, the mean SAT verbal score, and on the x-axis, the percentage of high school students in that school who take the SAT. So if you try and fit a straight line like this, you're going to have some problems. So it fits this stuff here and this stuff here pretty well, but here it starts to fit worse. Here it fits worse. All along here it fits worse. Not just fits worse, but it fits systematically worse. The line systematically overpredicts here and systematically underpredicts on the ends. Because this is a curve, the natural line is a curve. So if we could fit a curved line, we'd have a much better chance of doing things. Now think about what happens if you use a straight line when it's actually a curve. You might say, oh, my correlation is 0.5. When in fact, if you had a curve, your correlation would be maybe 0.7 or something like that, a much better correlation. Also, if you're using a straight line and trying to predict values, like what if you said, so given this prediction, we predict that if you had a high school where 100% of students took the SAT, we would predict that the mean SAT score would be like a 470 or something like that, or 460, because that's where that line goes, right? That line goes down here. So it should end up about there, more or less. And over here, maybe 465, a pretty low SAT verbal score. However, if you incorporate the curve, it looks like things just flatten out. It looks like maybe they're never going to get lower than about 500. So that's a bit of a difference. Our predictions would be wrong because we didn't incorporate the curve. So here's another example of a curvilinear relationship. We've got these car data that I presented to you before. We've got the price of the cars and the efficiency, the miles per gallon. Is this a curvilinear relationship? Well, let's try and find out. Let's fit a straight line to it. Now, fitting a straight line is just standard regression. That's what we're doing in this class. And if I just look at the straight line correlation, in other words, the correlation, any basic correlation is a straight line correlation unless you mess with it and make it a curved one. We find a reasonably strong association. R is that's supposed to be a negative 0.85. That is a very strong correlation. There, fixed. That's a very strong correlation. But it's still not giving us the best model of what's going on between price and miles per gallon, of what the association is there. So let's go back and fit a curve to it. Now, there are ways to do this in regression, and I did that. Actually, the way you do it is, if you remember doing polynomials in algebra, you have something, x equals whatever x squared plus whatever x cubed, etc. You just add an x squared term, and the regression formula in the mathematics will find the best curve, like one bend curve. So I did that, and that is the best fitting least squares curved line there. Now we can figure out the correlation for this curved line, and the correlation is actually stronger. It went from negative 0.85 to 0.95. Now I put a star there, an asterisk, because this isn't your standard Pearson correlation. It's the curved version of the correlation. It's correlation for a line with one bend, as in it doesn't do a snake thing with two bends, it just has one bend. The best fitting one bendy line, which is what we would do in this situation. So the straight line isn't doing it really justice. You can see there's deviations, vertical ones there, there's vertical deviations below the line here. But if we fit the curve, you'll notice those deviations are much smaller. The curve can now be closer to all the dots, so it's a better model. So when you violated that linear condition, your problem is that you're just going to underestimate the actual association in almost all cases. So it's just good for you to make sure that you find the curve, if there's one there. Non-normal residuals is actually related to that. That's condition number 2. The residuals, if you look at the histogram of the residuals, that histogram should be normal. This is just an assumption of the entire, what we call the linear model, which is a big, gigantic set of assumptions and conditions that underlie essentially everything we've done in this class, and quite a lot of the basic statistics you would get even in grad school or professional level. So let's look at the data MT cars, which is one of the data sets that's available in R. Here we have a plot of fuel efficiency, miles per gallon, by the horsepower of the car. You can see lower horsepower is more fuel efficiency, and as you get more and more powerful cars, they have less fuel efficiency. Now I think it's pretty clear there's kind of a curve thing there, and that's a good way to demonstrate this non-normal residuals thing, because one thing that can cause non-normal residuals is a curved relationship. There are other things that can cause it as well. So here's the line of best fit, and this is what the residuals look like. Now this isn't in order. You just take the residuals, the residuals here, and the ones down here will be negative, and the ones on top will be positive. Down here that has a big residual there. And just like any histogram, you stack them all in order and see how they fit. So these are the negative residuals. These are the residuals of the points that were below the best fit line, the regression line, and these are the ones that are above. This isn't really very normal. This is skewed to the right. So it might not be enough to make a huge difference, but it should alert you that there's a problem. And it is technically a violation of the conditions. The residuals should look nice and normal. This is too lumpy here. This lump should be in the middle, and it should kind of curve down nicely like a normal distribution. You can do a QQ plot, a normal distribution plot of the residuals as well, and you can see whether they're distributed nice and normally, and these would not be. So when you get non-normal residuals, you are violating the conditions, and when you violate the conditions, it means you might not be able to trust your results very well. Your residuals don't need to be perfectly normal, but the previous example is a bit of a problem. You probably should be more normal than that. Non-normal residuals might indicate a curvilinear relationship. They might indicate that there is non-constant variance, which we'll talk about in a second here. Or they might indicate a number of different problems as well. But either way, they're a bad sign, and you probably should not use the kind of regression we learn in this class if you're getting seriously non-normal residuals. If you have a question, is this normal enough? It's a little non-normal, then it's probably honestly okay, in my particular experience. When it's really non-normal, those residuals are just going to jump out at you. Crazy skew is usually the problem. Super skewed in one direction. Then you say, whoa, that doesn't look like a normal distribution. That looks more like chi-square or something. That's a crazy ski slope, long tail distribution. Then you have a big problem. Non-constant variability is another one of the problems. This is a violation of condition number 3. And this can be caused by skew in one or both of the variables. It can be associated with the problem, with the previous problems we've talked about here. So let's look in the support data set. the total number of miles that the participants reported that they traveled to their jobs every week, so whether it was a single job that was 100 miles away or whether they had 3 jobs and each of them was about 30 miles away or something, then these people would get 100. So who knows, they're driving to the island every day or something. But this is how much work travel you're doing, how much travel you're doing to get to your job, and then this is your GPA. In general, there's kind of a negative association there, but notice what's going on here with this. This is, if we fit the line here, there's a good deal of variability here, and then down here there's less variability, and here it's actually kind of all packed up on one side. We've got a problem here. We've got a problem that we've got skew, or we've got skew in one of the variables, the total miles traveled to jobs. And what that means is in this particular case, you've got more variability here and less variability as you go along. It might not be the biggest problem in the world, but it's a problem. So let's look at what those residuals look like. Here's the plot of the residuals. Now notice it looks like the reverse of this plot. Which I believe is because it's doing weird things with the fitted values. But either way, you can look and you can see it has the same sort of pattern here. We've got a lot of variability down here and less variability here. Now let's talk about outliers. It's not really covered in the previous examples, but it causes problems for sometimes the same reason. This is a great little comic about outliers that somebody else showed me, and it's great. So here we have an example from the support data set. An outlier is an observation that, as far as you can tell, really isn't responding to the same forces as the other observations in your data set. Sometimes you'll see it in a histogram, just one dot that's way out to the right or way out to the left, but sometimes you won't see it until you do the scatter plot that includes both variables in it. So in this case, when you do a scatter plot in some of the stuff in R, some of the functions in R, it will label which case this is. So this is row number 41. So this dot over here is a problem. It's very far away from everything else. Now, if an outlier is close to the middle, it'll have less of an exertion on the line, but if it's close to the end of the line, it'll have a big problem. It'll have a lot of influence on that line. And that's the problem with outliers. One dot should just represent one dot. It's like being in a democracy. One person should have one vote. But this is like the super rich person that has more votes than everybody else, and so they're pulling the entire political process toward them. They can buy votes. They can buy a bill, get passed through Congress, because they're so rich. It's Bill Gates of scatterplots or something. So you look at the correlation there, 0.83, and look at where the line is. Now what if we get rid of that item number 41? The correlation goes up, but also the line has shifted. So here it is without this, so with and without. The model is a different model with and without that outlier. That's the problem. That outlier is exerting influence. It has what the textbook calls leverage, too much leverage. So when we have outliers, I mean, you want to look for outliers, but you don't just delete them, because the problem is, what if this person is representing something that really was happening? Maybe there is something that happens that causes people who have ridiculously low English scores on the ACT, nearly 0, to have very high reading scores. Now I suspect that this is just an error. Somebody entered data wrong, or somebody was screwing around and didn't respond well on the questionnaire. But what if it's not? So we look for those outliers, these lost sheep wandering away. There are technical ways to identify outliers, but I say just look for them. And you mention them in your report, and it's a useful thing to rerun the analysis with them and without them and look at the differences. So if there's very little difference, then you don't have to worry about them. They're not affecting anything. But if there is a difference, and if that difference is big enough to matter, then you need to make some sort of a decision. Now for this class, you don't make a decision. You just say, I note that there's outliers. There you go. If I ever had you writing any reports, which I don't think I will, you would just note that there's an outlier. Or on an exam, you'd say, I notice there's outliers that might affect things. Try and understand how it would affect things. Now in general, beyond this class, let's just consider that outliers can sometimes make a big difference. That's why we rerun the analysis with and without the outliers, to see how much of a difference they're making. If the outliers don't belong, then we delete them. But making that decision of whether they belong, that's beyond just statistics. The statistics can help you decide that sometimes, but sometimes they can't. A lot of times, this is something like a data entry error. Like I had actual humans entering the data for the support study, so for that row number 41 person, I should go back and check and see if their value was entered correctly. I still have the papers, I can dig into those, and I can find out if that's correct. There can also be random responding in surveys. People just screw around and just click buttons on the online surveys or try and spell their girlfriend's name with the bubbles in the bubble sheet or something. They're not actually responding to the questions. And because their behavior is influenced by something different from everybody else's, in other words, by random, screw you, I don't want to be involved in this study, motivations or something, then their answers can sometimes be outliers. So if that's the case, you delete them. You delete those observations. Or if the cases actually belong to a different group. So I did a study of sex offenders, and after we got the study done, we realized there were like 70 sex offenders who were male, and there was one who was female. Sex offending is strongly related to sex and gender. It has something to do with it. Therefore, it would make sense for me to throw out the data from the person who was female. It really would. I don't think her responses are going to be driven by the same factors and the same motivations necessarily as the male offenders. So she would be an outlier with a lot of her answers, and I should get rid of that outlier. However, if the data do belong, then you can't delete them. So sometimes weird things happen, and sometimes there are things happening in your sample that you're not aware of, and the outlier might be the data that lets you know there's something else going on that you need to be aware of. If you just throw that data out, you'll be missing it. You won't be letting it influence things honestly. If it's part of your data, you have to let it influence the data. One of the things you can do is redo your sample or redo your study and get a much, much bigger sample, because if there's one outlier and it really does belong with your data, then if you get a big sample, there will be a lot of things, a lot of dots on the graph, a lot of observations similar to that, and it won't be an outlier anymore, and then you'll be able to see the patterns. There really aren't any easy solutions in what to do with outliers. You just kind of have to think every case through very carefully, talk to all your friends, all your colleagues, see what you think you should do. Now let's talk about another problem with correlation and regression, restriction of range. What this means is just measuring some of the true range of one of your variables, x or y. And what the problem is that can misrepresent relationships. I'll give you some examples. So what's really common is that the correlation between two things appears weaker than it really is. That if you measured the whole range, you'd see a strong correlation, but you're only measuring part of the range, so you only see part of it. The classic example that was given to me by a friend of mine years ago was, what if you were studying like rushing yards in college football people on an offensive line, but for some reason the only people you included in there would be linemen whose weight was below 250 pounds. Well, yeah, you might not see any relationship between rushing yards and the person's weight, right? But if you let everybody appear, then you'd get really big people, and you might see a really strong relationship. You might see that the heavier people had better rushing averages. So if you only include some of the observations, and they're systematically biased towards one end of the scale, you could end up with this problem. So sometimes you're not even aware of the full range. Sometimes you use a questionnaire or some other kind of measurement that doesn't measure the full range. What if you are measuring IQ with a regular IQ scale, but you're measuring it in the gifted and talented classes at the local schools? Well, you're not going to be representing the people on the top end. Regular IQ scales have a hard time making distinctions between people who have very high IQs, and so we call that a ceiling. Or if you're using a regular IQ scale, but you're measuring it only in a school that specifically caters to people with developmental disabilities, so people who have serious mental retardation, serious learning disabilities, stuff like that, then you might get people kind of clustering on the bottom of the scale. This can also happen with dishonesty and shenanigans. If you want to know how to lie with statistics, one way is only use a portion of the range of one of the variables. So you can sometimes claim that you're being honest, but you're not because you didn't include things. So here's an example that we've looked at before, the amount of alcohol you drank the previous night and then your test score at your class the next day. Well, if for some reason you didn't just ask how much alcohol people drank the previous night, but you just said, here are your options, 200 milligrams, 200 milliliters, 250 milliliters, 400, and you gave them like a drop-down list, and it only went from like 250 milliliters to like 800 milliliters, you'd get this pattern here. And you might have a negative relationship, I don't know, but it might be hard to find a relationship between just the dots that are in this circle. It looks like there's almost no relationship between them. clearly there's a relationship if you included all this stuff, but if you were only including the very middle of that scale of this variable, then you might not find that relationship. So this is what that looks like without the ends. It's kind of hard to see a relationship there. So here's another example. Let's say you're looking at happiness as a function of national corruption. Let's say zero corruption is indicated by 0, and the people who made the scale said corruption is bad, therefore the values are negative. Okay, great. But what if for some reason you only managed to include a number of countries that had really bad corruption, and you didn't include all the other countries? You just got a bunch of seriously bad countries. Well, now it's not clear. What's the relationship here? It might be kind of positive, but it might not show up at all because you didn't include all the rest of the data. If you're only measuring one portion of the scale, just negative 60 and below here, you might not see the relationship at all. So here's another example from my data that you might be familiar with at this point. Punishment attitudes towards sex offender, the sex offender who was in the vignettes, as a function of the number of offenders a person has personally known. So what if for this study, the punishment attitude study, we only used the undergraduates who would have known very few sex offenders personally? So this is just the undergrads. So the sex offender in the story committed a sexual offense. So we're asking people, how many offenders have you personally known? And the highest number among undergrads at Ohio State in 2000 and whatever this was 10. And then we say, toward this particular offender, this sex offender that you saw in this vignette, how much do you think this person deserves punishment? So you see that it's a horribly skewed variable, the number of offenders known, and so that leads to restriction of range. You have variability problems here. This has got some problems. But anyway, it looks like there's essentially no association. There's the regression equation, and the correlation is close to 0. It's negative 0.05. But now we add in the treatment professionals who were also in the study. Some of them knew, well, the highest number, one person said that he or she knew 8,000 offenders personally, and that's probably realistic. There are probation officers, there are lifelong sex offender therapists included in that group. So now we have a big range. I even had to do a log scale because it was so skewed, it was just ridiculous. So this is the person who knew 8,000 people, but this is the log of 8,000. So it's 8 point something, 9 point something. So anyway, now we get a clear negative relationship. The more offenders you've known, the less you want to punish sex offenders. The relationship there is much more clear. It's a strong relationship. R is negative 0.52. Now you should think, does it make sense to have one group of undergrads and one group of professionals and lump them together? That's a separate issue. I just wanted to show you what happens with restriction of range. If you're only including people who have known very few offenders, you might not see any relationship. But if you include people who have known lots of offenders, then you will see a relationship. The no relationship might be because you just restricted your range. And now the final thing we're going to talk about is extraneous variables, sometimes called nuisance variables, lurking variables, confounding variables, variables that make me feel very bad about myself, etc. And this means any variable that is influencing your dependent variable, your response variable, but that you are not aware of. These are the worst things. It's the unknown unknowns, the things that you don't know are influencing your data. These are a huge problem in correlation and regression analysis. Some people would suggest they're perhaps the biggest problem. So here's some examples. I've mentioned this in class, but the number of churches in a town and the number of crimes committed in that town are strongly positively related, but not because church causes crime or crime makes people build churches, but because a really obvious variable is left out of that, population of the city. That's why for these answers or these examples, usually we will say per capita, churches per capita and crimes per capita. And as soon as it's per capita, I don't think there's any serious relationship anymore. Ethnicity and IQ. For years, we've known that there are associations between a person's ethnicity and their IQ. So people who are African American and Hispanic American get lower IQ scores on average than people who are Asian American and European American. But an awful lot of that, with the exception of the Asian American high IQ effects, essentially totally disappears when you talk about a cluster of variables associated with socioeconomic status and education and the stresses of stigma and prejudice. So, if we could somehow equalize those things, if we could somehow make the Hispanic people and the black people from LA not live in socioeconomically deprived areas and let them have schools that are the same quality as your average school for Anglo people in Minnesota, then that association would essentially disappear. And in fact, there are some weird studies like that. There was a study a few decades ago in maybe Tennessee where a housing project was going to be shut down, and it was almost all ethnic minorities, at least in the U.S., ethnic minorities and very low-income people in that project. And there was some sort of state money available, and these people, a random subset of them, were relocated to middle-class suburbs and followed up. And basically, their education and their children's IQ and all these variables that we've tracked and that some people thought were ethnicity variables, within a generation they looked just like everybody around them. People started to look like the people in the environment that they lived in. So this socioeconomic status, education opportunities, prejudice and stigma, those are extraneous variables. As far as we know, there isn't an association, a consistent association between ethnicity and IQ. But there is an association between the amount of money in your life and the quality of your schools and stuff like that and IQ. There's also something called the Hawthorne effect that screws people up from time to time. You do an experiment and then you say, woohoo, my experiment worked. I found differences between the control and the experimental group. This is why you have to do double-blind experiments, because if people realize what group they're in, like I'm in the control group, I'm in the experimental group, even if they don't intend to, their behavior might change. This is extremely important for psychology studies because some of the stuff we study is really delicate, and very small changes in the person's awareness could mask our effects. So this is another example of an extraneous variable. You think your experimental manipulation is responsible for the changes in your dependent variable, but in fact, what's responsible for it is people being aware that they're in a study. So this leads us to the final slide here, and it's really important. Correlation and causation. You might have learned to chant this thing that says correlation does not imply causation. That's actually kind of false. It does tell us something important, though, because X and Y are correlated. That's not sufficient evidence to say, therefore, X causes Y. However, correlation is evidence for causation. It's just not evidence for the exact kind of causation that comes to mind first, and you might not be able to figure out what the causation actually is. There's a lot of different kinds of causation. There's a lot of different ways that causation can happen. If X and Y are correlated with each other, some kind of causation somewhere is happening. Our understanding of a deterministic universe suggests that this is the case. But it could be ridiculous. They're correlated because way back in the Big Bang, two hydrogen atoms got together. It's probably not that far back in the chain, but it doesn't mean X causes Y or Y causes X, although those are possibilities. So if two variables are correlated, one reason would be because changes in X cause Y to change. Or it could be changes in Y cause X to change. So whenever you see a correlation, please do this. Try to think to yourself, rationally, think through the variables and think, how can I make this work so that X causes Y? Can that make sense to me? Then don't stop there. Go to step 2, and there are 3 steps. Step 2, and think, how can I think that Y might cause X? And almost all the time you can come up with a really plausible one of those too. Then think of this one, the third variable problem. How can I think that some different variable, which is supposed to be Z, anyway it's Y here, some variable that's not X or Y could cause both Y and X to change. So, population causing increases in both crime and number of churches. Now, the real world might look a little more like this. Not that this is my specific model of the world, but things influence each other all the time. And when we take a little selection and you say we're looking for associations there, that can only ever be a part of the piece or a part of the whole. So we find these little sections and we say, oh, X is correlated with Y. And it might take a lot of different studies and a lot of careful thinking to try and figure out what other variables we should measure. When we measure those other variables, then we learn about more variables we should measure. We should learn about variables we should not measure because they mask the effects of other variables, etc. This gets very complex, and 2 simple variables doesn't usually resolve the situation. So, hopefully this has convinced you that A, correlation does not imply causation is not technically a true statement. Correlation usually does imply causation. But B, the causation could be something that we are not going to figure out anytime soon. So it is pretty dumb to say X is correlated with Y, therefore X causes Y. However, it's equally dumb to say there's no causation. Correlation can't tell you anything about causation. Correlation tells you something about causation. It just doesn't tell you enough. The end.